Okay, our next talk is on porting applications to high-performance imaging DSPs by Chris Rowen at Tensilica. And Dr. Chris Rowen is Chief Technology Officer of Tensilica, which he founded in July of 1997. He was a pioneer in the development of RISC architecture at Stanford in the early 1980s and helped start MIPS Computer Systems in 1984, where he served in a variety of functions, including Vice President for Microprocessor Development. When Silicon Graphics purchased MIPS, he became the technology and market development leader for Silicon Graphics Europe. In 1996, he became Synopsys' Vice President and General Manager in the Design Reuse Group. And Chris received a BA in Physics from Harvard, an MS and PhD degrees in Electrical Engineering from Stanford University. So, welcome, Chris.
Thank you.
One moment, please.
Yeah, I haven't listened to that bio for some time, so it's interesting and perhaps poignant how full circle it is. Coming back again and again into the processor business and coming back again and again into the EDA business. Because the big news of this week is, in fact, that Cadence has just finished its acquisition of Tensilica this week, so that we have become now, I think, the cornerstone of advanced IP within the Cadence portfolio. And it's probably appropriate to think about how these different pieces of the whole design flow are hooked together as we think about the role of imaging. So I'm not going to talk much at all about what specifically Tensilica is doing, but I think there are a set of challenges about porting applications into efficient processors which are particularly poignant when we look at imaging. And imaging is really a magnification of some of the issues that occur in other domains. They occur in audio, they occur in baseband, they occur in security and networking, but they really are particularly dramatic here. The application drivers, of course, are in general the things that we've all been talking about, and there are a lot of fun applications, which is, I think, part of the excitement that is really captured by imaging. I think the particular focus that's really driving it into everyday use is these really high volume applications in things like smartphones, in games, in televisions, and in cars. But especially when you consider the demands of something like a mobile application processor. You see it so poignantly because here's something where you want a revolution in capability, which may require 10 or 100 or even 1,000x the performance that you're used to getting out of imaging because of the algorithms. But at the same time, you're trying to fit into a power envelope where your total sustained budget for doing this function may be just a few hundred milliwatts. That's kind of a grand challenge problem. And it's incredibly diverse and has a high rate of change of algorithms. So it's important to be able to think not just, can I get the functionality somehow, someday onto this platform, but can I get it there quickly and accurately, yet still be in a world where I am satisfying a need to have millions of operations per second for a few microwatts. In fact, one of the ways of looking at how hard the problem is to compare the rate of growth of raw silicon capability versus the kinds of demands that you actually see transforming imaging. So, we have our old friend Moore's Law, which these days, according to the ITRS roadmap, means that we're getting density improvements at a rate of about 25% per year. By contrast, we have half a dozen major movers in terms of forcing functions for increased imaging performance. It could be the migration from 5 and 8 megapixel still images up to 20 megapixel. It can be the transition from trying to do this advanced image processing on still images to doing it on continuous HD video streams. It's the migration from HD 1080 up to 4K by 2K. And it is the explosion of new video processing algorithms, be them feature extraction, tracking, identification, augmented reality, all kinds of things, which mean that the sophistication of the algorithms is growing dramatically in terms of the number of ops per pixel, let alone the pixels per second that are driving it. So if you take even a subset of those things happening, say, over the course of the next decade, that translates into something like a required doubling of imaging performance about every year. And of course, your power budget stayed fixed. So the implication is that there is a growing gap between whatever you could do in an architecture just by scaling it up, adding more cores, turning up the clock rate, and what you probably need to do if you're going to have a place at the table in imaging. And that means that there's going to be a lot of new architectures that come into the picture, and therefore the problems of porting to architectures are very much front and center. When we look at how you are going to be able to bridge the gap, you have one big friend, and your big friend is there is, in one form or another, in most applications, a high degree of latent parallelism in the imaging task. The job in porting, the job in architecture, the job in systems is to figure out, well, how are you going to exploit that parallelism? And there are really half a dozen basic mechanisms at work in order to get the performance needed to keep up. First of all, there are techniques like issuing multiple instructions at the same time. Now, sometimes in general purpose processors, this is superscalar out-of-order execution. In other kinds of things like DSPs, this is literally VLIW, where an instruction bundle has multiple operations encoded in it. Each one of those operations may in fact itself be a vector. That is SIMD operations, where you're going to do that operation on a lot of data at once. You are going to see compound operations where you build a pipeline that doesn't do just a simple risk operation, an add, a shift, a multiply, but does a sequence of those things. A multiply, a normalization, an add, maybe some saturation. And those compounding of operations are the things that are most imaging specific, because they typically reflect the imaging data types and the typical patterns of operations that you will find together within an imaging application. You have, of course, an opportunity for multi-core, so many engines working in parallel to do the task, limited, of course, by the silicon budget and by the size of the individual cores. You have the essentially pipeline parallelism that plays out in terms of being able to crank up the clock frequency in order to be able to get more throughput, though sometimes at very significant price and power. So some of these help energy and peak performance together. Some of them are really more about just increasing total available performance. And finally, and very importantly in imaging, you have inherent potential concurrency between the memory system and the operations. In fact, for most of these things, unless you are able to fully parallelize what's going on to bring frame data into the processor and the processing of it itself, you're probably sunk in terms of throughput and efficiency. So these are going to be really at the heart of what you're trying to find when you are porting an application, particularly when, quite naturally, your goal is to get from a reference implementation that may have been developed in OpenCV, in floating point, on a big PC with a ton of gigahertz class cores, down into something that's going to run in a few hundred milliwatts. So there are a wide variety of choices, and this isn't intended to be exhaustive, but to really give you a little bit of a sense of some of the major choices that are out there. Of course, for many of these platforms, there are quite good CPUs that are available, often with some degree of SIMD execution units intended for media processing. So they have a wide range of different data types, though really a lot of these are oriented towards being good control CPUs, which means their most natural data type is 32 bits, occasionally 64 bits. They do support some vector operations, SSE, neon, that gives you modest degrees of parallelism there. And you typically have some basic multi-issue. And these cores are big, so you don't get that many on a chip, 1 to 4 cores. They tend to be pretty high energy per imaging op. And the sweet spot is when there is either a lot of control compute that needs to be done relative to the imaging compute, or where really you care much more about the ease of migration than you do about efficiency. GPU is clearly a step towards exploiting more parallelism, but GPUs by and large have a little bit of heavy investment in floating point, which can be either a good thing or a bad thing. It can be a good thing in the sense that some imaging applications started life as floating point and don't really want to move on. On the other hand, floating point is significantly more energy intensive, on the order of about 4x more energy per op than, say, dropping down into 16-bit fixed point. So it's clearly overkill from a computational energy standpoint in many, many circumstances. So the energy efficiency tends to be sort of medium. You do have a lot of latent parallelism in the home application of GPUs in 3D rendering, which means that you tend to have a pretty rich degree of resources available, albeit at fairly high energy, so that you can get higher peak performance typically out of a GPU subsystem than out of a CPU subsystem. Then there are hardwired function blocks, and these are incredibly varied. They have the advantage they can be exactly the bit resolution, the degree of parallelism, the specialization of operation that you want. It leads you to quite low energy optimization. But porting means designing. It really means, for the most part, having to get down and dirty and working out in gory detail the fixed function that's involved. And it has the significant disadvantage in most platforms that in order to change the algorithm, you're going to have to change the logic, which translates for high volume into silicon spin. So the time to map a new algorithm is measured in typically years rather than the minutes that you'd like to have. And so the imaging DSP plays a role within this spectrum, providing typically a wide variety of data types, but more focus on the, in many cases for high volume, on the fixed point data types, high degrees of parallelism with some combination of parallel cores and wide vectors, and really fairly well suited to complex imaging, so long as you are willing to take on the task of porting, which varies between trivial and highly non-trivial. So when we think about, in general, what it takes as you are mapping down to these more performance and efficiency-oriented platforms, there are some general things to think about. And I would say, first, one of the first things to think about is what is the data type and resolution that's really required by the application. Because clearly you would like to use the lowest resolution, highest parallelism data types that are available in your platform consistent with target output quality. And you really have to measure that target output quality. You can't just sort of say, well, I don't know, so let's leave it in floating point. Equally, you can't say, I don't know, so let's make it all 8-bit. Because you're likely to be disappointed one way or the other by saying, I don't know. So making the measurements to actually look at SNR or bit error rates relative to the reference application is critical. Second, it is particularly important to identify sequential dependencies in the algorithm, particularly where there are recurrences. For example, if you're sweeping across some image, accumulating errors or accumulating sums, you need to figure out how to break those sequential dependencies, often by transposing or transforming or gathering the data in a way that allows you to do large parts of the transition or the computation in vector parallel form. As some of the other speakers have mentioned, the data access is critically important in order to be able to get even remotely reasonable performance and to exploit the parallelism between compute and memory reference. And this is one of the places where the original expression of the algorithm can often get in the way. And if you take something like OpenCV, its basic paradigm is you're going to start with a frame, you're going to do one transformation to it, and you're going to put it back in the frame in memory. And then to do the next step, you're going to read the whole thing again, do a transformation on the whole frame, and write it back into memory. That clearly ain't going to work in most platforms which have finite memory resources close to the computation. And so it is going to be, you're really going to need to think about how that gets restructured for tiled access so that you can bring in a series of chunks, a pipeline of chunks flowing in as a stream, typically of 2D tiles, exploiting either cache prefetch or DMA resources to hide that. And finally, as you launch into the overall porting exercise, it's important to understand what kind of library resources you have available, because typically you'll have the ability to run OpenCV, but you'll also have a range of more optimized platform-specific libraries that keep you from having to reinvent the wheel. And all of these other things that allow you to run large-scale applications in your simulation environment or in your FPGA environment are going to be key. And I've listed a whole bunch of things there that are useful and you should look for. Now, what does the sequence look like? What are some of the steps that you want to take on? And here is at least one shot at looking at some steps. First, measure what you got to start with. Measure not only the cycle performance, the memory utilization, but also collect the data on exactly what the image resolution is. What's the incoming data? What's the resolution of the outgoing data? So that you can look at each step of the way at the comparison to that reference to make sure you're staying between the guardrails in terms of image quality. Second, look at the data types. One of the big gains is going to come here if and when you can move away from floating point representation into a fixed point representation because of the throughput and energy ramifications of it. And in our experience, it's very often possible to do this. Sometimes you have to think a little bit cleverly about how you're going to retain the full precision of your fixed point data type as you move through. But in importing a lot of code, we've generally found that having a choice of 8, 16, and 32-bit gives you enough resolution in enough circumstances that you're generally fine. But you will have had to have looked closely at certain critical steps where, for example, you can leverage normalization operations, or where there are numerically unstable calculations that you might be wanting to do to make sure that you don't lose a lot of precision when you go through a float to fixed conversion. And then you have a process of looking at how you break sequential dependencies, loop dependencies, restructure data access in order to move dependencies from inner loops to outer loops. Because the inner loops you really would like, under most architectures, to have very uniform access, as uniform as the algorithm fundamentals allow. Now, this is usually pretty simple in terms of image enhancement algorithms where you have very commonly unit stride access. You have to be a little bit more clever, for example, in some kinds of vision applications where you're effectively going through a region of interest filter, and the regions may become more scattered and smaller, and there may be opportunities to regather those data points together by a variety of means. Lookup tables of various kinds show up in lots of places. I think because imaging is full of nonlinear approximations that tend to get translated into one kind of lookup or another. Sometimes it's explicitly a complex function, an exponential function, which is written explicitly into it, and sometimes it's translated or captured in the form of a lookup. But as you go to parallelism, parallelizing lookups is one of the big challenges, and it's going to be one of the things that may be important in the ultimate architecture choice that you make for the target platform. But these deep table lookups can otherwise be a very significant bottleneck. So you need to kind of address them really up front in planning the porting process. And then you get to the actual mechanisms of vectorizing code. With a good vectorizer, there's a lot of code which will simply compile and run with automatic vectorization. That the compiler knows how wide, knows what the constraints are, can track down potential aliasing of pointers and help you solve those problems. Or in some cases, you may want to adopt an explicit vector data type, where it's otherwise C programming, but the fundamental objects aren't ints and shorts, but vectors of ints and shorts. In a few cases, the algorithms are sufficiently bizarre in terms of their data access that you need to operate explicitly on the elements of vectors and do reorganization on the fly, and that typically comes in about this stage. Rather late in this process, then you get to start to look at things like how efficiently the parallel issue in your machine, be it VLIW or dynamic superscalar. This is typically something which is handled pretty well by the compiler, and so only in the most extreme tuning where you may have some choices about operation selection that can interact with the VLIW packing comes into play. But the impact of this, that is getting from 1 or 2-way sustained issue to 3 or 4-way sustained issue, that's maybe only a factor of 2, whereas vectorization may be helping you by a factor of 16 or 32 or more. So vectorization is the big hammer here. The exploitation of a tile manager, a tile structure in the code is not a small deal. It's a very big deal. But I think we've tended to find that porting the inner loop computation first and then coming back and seeing how exactly that now wants to do its tile level handshake with the memory system is kind of can wait until a little bit later. Very important, but can happen somewhat independently of what's going on with the optimization of the inner loop. And then all along here, if you have access to a multi-core architecture, you're going to want to exploit that. We've typically seen that first exploiting maximizing performance for a single core and then going multi-core is a reasonable strategy to take in terms of optimizing. But you probably wanted to have thought about key issues in multi-core. In particular, is your basic strategy to subdivide the images and have each core working on a different sub-image, or to pipeline the computation where each core is doing some stages of computation on the whole data stream. That will help you determine what is driving the optimization of some of the other pieces. So now let's look briefly at a medium complexity problem. Here we're looking at the optimization of a bilateral filter. A bilateral filter is kind of interesting in that it has some classic bulk processing characteristics like other Gaussian filter kinds of operations, which are essentially fixed coefficient. That is, the coefficients may depend on the distance, the location of a filter tap relative to the pixel output of interest, but doesn't really depend on anything else. The bilateral filter, which has this very nice edge-preserving property, has a really key component, this function g, which adds a pixel intensity difference factor to it, so that when you're weighting this filter, you're not only looking up a coefficient based on the location of the tap, but you actually vary that value based on the actual content of the image. And this makes it much more difficult to parallelize. So you have these different components within it. Standard coefficients can be pre-computed, but the intensity kernel is hard because of this adaptive nature. And essentially, it looks like a different computation, a data-dependent computation at each pixel location. So the other parts of the filter can be easily vectorized, but this one component is a significant issue. And what we found, though, was that by using some clever data reorganization, we could essentially emulate any depth of table lookup and do it in parallel. In this case, do 32 table lookups in parallel. So as we looked at the overall impact, we started from a baseline implementation, just first optimizing the code for good fixed point implementation. And so our baseline is already fairly well optimized. This isn't floating point, this is fixed point. And then looking at vectorization. And vectorization of all of the computations, except the intensity coefficient part, gave us about a 10x speed up. So if measured in operations per output pixel, we go from several hundred to tens of operations per output pixel. And then we came up with this way of using this parallel table lookup method to vectorize the intensity lookup function. And that got us essentially another factor of 30. So overall, we get down to just a few cycles, a few operations, essentially a few operations per pixel. A few cycles per pixel. Now, accuracy still matters. And so one of the key choices that we had to wrestle with is how much quantization are we going to allow in this table lookup? And what's the impact on the final quality of the image? And in fact, we looked at three cases, basically quantizing to 128, to 64, and to 32 intensity levels for that pixel difference. And, excuse me. And what we found, in fact, is that we had very high PSNR levels. So PSNR here, so this is varying from 59 to 63 dB of signal to noise ratio. To put that in percentage terms, that means we were choosing in terms of average pixel error of things on the order of 1 to 3 100ths% of error relative to the full resolution, original, non-quantized table lookup. By almost any respect, any one of these is totally undetectable in the final image. And so we can reasonably say, okay, this process brought us to about a 300x speed up for a single core versus a single core baseline RISC architecture. So reasonably successful porting exercise. I want to mention in passing the role of development environments for doing this, because porting is an engineering exercise where you really want it to be very productive. And productive means not only that you allow it to move fast, but you get insights that allow you to make good choices along the way. And some of the things that have turned out to be quite useful within this is, of course, good source level C tools, good libraries, and good visualization of what's going on at an intimate level in the inner loops. Because to a very large extent, if you're really targeting maximum performance and minimum efficiency, you're going to end up looking at that inner loop code pretty closely. Now, it should all be written in C, but you still may be looking at how good is the code generated from that C, because that may tell you a lot of things about, well, did I get the vectorization I want? Did I get proper exploitation of parallel instruction issue? How is my memory system working? And visualization techniques like pipeline visualization, where you can see exactly all of the stall behavior in the pipeline for every instruction in the inner loop and all of the operations that get packed together into the inner loop, is going to turn out to be an important part of the insight. Now, when we port, we use a combination of virtual prototyping in fast simulation, where the simulator is running at tens of millions of cycles per second, and FPGA, whose speed is actually kind of rough order of magnitude comparable. The difference being that you have all this great visualization capability and instant turnaround for the virtual prototype. Of course, the physical prototype, the FPGA, it's easy to really hook up sensors and watch live video and see live output. And you can debug a lot of things that are subtler than what you'd be willing to do at this level. I think this really reinforces the notion that actually looking at the code can be important. And it's important because it's going to tell you a lot about how well you exploited it. It's going to tell you what kinds of operations. In this case, we have some of the quantization operations. We have the table lookup operation. We have multiplies. We have absolute difference operations. There's a lot of imaging-specific things. And we're typically looking, is it fully vectorized? Are we getting close to the VLIW packing limit? Are we near either the multiply bound or the load store bound? Those are key considerations. So that's what we've been finding in porting as we've worked across now a very wide range of different applications. Just a word, who is Tensilica? In fact, now we can sort of say who is Cadence as of this week. But Tensilica is a very key part of what Cadence is evolving to. And we have become really a leading provider of embedded DSPs, licensing very broadly across a range of different heavy lifting, data-intensive applications. We've now shipped close to 2.5 billion cores. We have been long active in imaging and video, though generally where customers were coming up with their own proprietary extensions to our Extensa architecture. I think that translates ultimately into about 750 million cores out there in the field today, Extensa cores used in digital cameras, printers, and video subsystems doing imaging stuff. And just a few months ago, we launched IVP, which is a general purpose, highly parallel image, video, vision DSP for this class of applications. So as a short wrap up, imaging, as you guys understand, has an almost infinite appetite for computing power. It has the key characteristic of rapid change in algorithms. That is, people are inventing new things that they want to do rapidly. And that puts a lot of focus on ease of porting. So you have this ironic situation where the rate of change is very high, so you want to port easily. And the gap in terms of energy and cost between the dumb implementation and the highly optimized one is not a factor of 10. It's factors of hundreds or thousand. And so there is more at stake in doing good porting. To do successful porting does require a structured methodology. The bilateral filter is just one fairly simple example. So we wish you happy porting. And I'll take a few questions. Yeah, so the question is, I didn't talk really about FPGAs. How is FPGAs part of this solution? To paraphrase, is that all right? Okay, so in general with Tensilica cores, we have probably a large minority of our customers who, in addition to doing virtual prototyping and simulation, also do FPGA prototyping of their systems or of their cores. And in fact, the processor generator, which automatically creates all these variations of the core, spits out an FPGA netlist as just one of the hardware byproducts. So source RTL, pre-synthesized FPGA netlist. And so lots of people go to FPGA netlist. We, in fact, have our own FPGA demo and development board. In fact, that's over in the demo room there with all of the appropriate interfaces and development libraries for imaging wrapped around it so that we can prototype algorithms on it easily. And the trade-offs are sort of observability versus authenticity for virtual versus hardware-based prototyping.
Which software standards do you see as important for porting embedded vision algorithms to your hardware?
Yeah, well, I mean, it's a many-layered question. The question is, what software standards do we see as important? You know, it's clearly a many-layered process that people go through. And when we launched into this a few years ago, we made the assumption that OpenCV is where it was, where it's at, because that's where algorithms get developed. And as we dealt with more and more real embedded software providers, we were surprised to find that they had long ago sort of moved their algorithms past OpenCV. Not meaning that OpenCV isn't important, but that the gap in performance between prototyping something in OpenCV and porting it onto any one of these platforms is a sufficiently large gap that you want to have really thought carefully about what's the efficient memory movement, what's the efficient data types, and really taken some steps beyond kind of that reference implementation. Even before you think about the specifics of porting to one imaging DSP or GPU or another. And so when we provide an environment, yeah, we have OpenCV that you can run it as a reference on the simulator, and then you can do piecewise refinement of it. But typically there's such a large data transformation and often an algorithmic transformation that's required that the most important thing is in some ways the more optimized kernels that sort of show how you get the maximum performance for an algorithm which is already in the right basic data flow in order to keep the average porter from having to know, what does it take to do optimized quantization of the lookup tables. I mean, this is interesting to show sort of what's going on inside the sausage factory. But ultimately, with the libraries we have, we're hiding much of this detail so that they have this higher level, but not typically OpenCV in its canonical form because there's still a large gap there.